Going to be finishing up chapter 14. So the last thing we're going to talk about in chapter 14 is linear regressions. Okay. So when we talk about a regression line, we're talking about a line that's a straight line that kind of illustrates the relationship between two quantitative variables. Okay. So for example here is a data set of miles driven on a vehicle and the value of that vehicle. So if we look, this regression line here is describing the relationship between the mileage on the vehicle and the value of that vehicle. Everybody okay with that idea on what we're looking at in the picture? So the yeah. Oh, okay, 30 minutes.
Thank you so much.
The idea here, when we draw this regression line, is we want to draw this regression line so that it's as close as possible to the entire data set. The way that we measure how close it is to the entire data set, or one way we can, is by looking at the residuals. So that's like the y distance from the data point to the best fit line. So we look at like all of those little distances, and we use each of those distances to like make a square. So if I'm looking at this data point, I'm going to look at this distance from the data point to the regression line, and I'm going to build like a square that has all side lengths of that distance. Right? Everybody okay with that idea? I'm going to do that for every single data point, and then I'm going to try to move this line around so that the total area for all the squares is minimized. Okay, that method is called a least squares regression line. So that's the idea of what your calculator is going to be doing in the guts. Are you going to have to do this by hand? No. That actually, the optimization problem of like minimizing the areas actually is a rather difficult problem and way beyond the scope of this kind of a class. But that's what the calculator is doing in its guts. All right. So let's talk about like an interpretation of what we're getting. So remember, this regression line is a model, right? It's going to be something I can use to predict the value of the vehicle based on how far it's been driven, right? So if I could, like if I said, how much is a vehicle with 100,000 miles on it? I could plug in like 100,000, and out of it will spit out like a Y value, right? The value of the vehicle. So in context here, our regression line is going to be a y equals mx plus b equation. We use this y hat on the y. That's like our predicted value. Since we have x and y coordinates also, it gets kind of muddled if I don't put like a special symbol on this being the predicted value of y. M is the slope. So that's the amount that y is predicted to change when we have a change of 1 unit of x, like an increase of 1 unit. And b is the y-intercept. That's the value or the predicted value of y when the x is 0. Everybody's okay with that idea? Just like y equals mx plus b, like from algebra 1, right? big deal. And a residual then, we talked about what a residual is a moment ago, but that's just the difference between the observed value and the predicted value. So just observed minus predicted. So if you looked at that same regression line we were looking at earlier, talking about the value of a car, I've drawn in like the residuals. See, these vertical distances are the residuals. Everybody's okay with that? Okay. So let's practice interpreting the slope and y-intercept, what those mean in the context of a problem. So this situation, we have a scatter plot with the regression line shown below represents the relationship between the average number of points scored per game, that's our x value, and the number of wins, that's our y value, for 12 college football teams in the SEC. The equation for the regression line is y equals 0.37x minus 3.75. If I ask you to interpret the slope and y-intercept in context, what should you say? No, it'll be a sentence. Interpreting, let's start with the slope in context. You're close. So the slope is a rate, right? So now you're doing the y-intercept. We're starting with the slope, though. Hang on to that answer, because that's, well, I'll want that in a second.
The more points per game you have.
But you haven't used the number for slope.
For every
So it starts for an increase in 1, and then whatever the x value is. So what are our x's measured in?
0.3.
Okay, so an increase of 1 points per game leads to a predicted, is it going to be increase or decrease? Increase of how many wins? 0.437 wins. Everybody's okay with that? So start with like a positive change in x of 1 gives you a slope change in y, right? So scoring 1 more point a game is basically worth half a win. That's what we're saying. Does that feel okay? Now, if I want to interpret what does the y value mean in context then? Joey. Good. Now you'd say 0 points per game, because, right, the x's aren't just points in the season, but 0 points per game. You should win negative 3.75 games. Now, does that make sense? Not really. Who can win negative games, right? What's the least amount of games you can win? 0. But, like, that's okay, right? Like, your model doesn't necessarily have to make sense over the entire possible domain. Similarly, if there's only like 14 games in a season, if you scored like 70 points a game, the model would probably tell you should win like 18 games or something, and that's impossible because no college football team is playing 18 games in a season. You know what I mean? But that's the idea. Everybody feel okay with interpreting that? How to do that? We'll practice again a couple more times so you get another crack at it. So it says calculate and interpret the residual for South Carolina. So South Carolina, it says, scored 30.1 points per game. and had 11 wins, and we're still using the same model from the previous page. So how do I do that? Oh my God, what happened here? Okay, it's just going to be that way. So what I'm going to do is I'm told I won 11 games. Oh, that's fine. I won 11 games, right? That's that observed. And then I'm going to subtract from that my predicted. So my residual is rounded to 3 sig figs, positive 1.6. So did South Carolina outperform or underperform their prediction? Outperformed, right? They won 11 games. The model predicted they should win 9.5 or so. Let's think about sports fans here. Let's think about how that could have happened. What could have been going on that allowed South Carolina to outperform their predicted value of wins? Okay, so if the other team's not scoring, what does that mean South Carolina probably has? Well, a good defense, right? So this is only measuring one side of the ball. It's only measuring points scored rather than points allowed. One might surmise that maybe South Carolina has a very good defense and they're not allowing very many points. And then as a result, they can still win games when maybe otherwise if they had an average defense, they wouldn't, right? What else could have been going on? Okay, maybe, sure. A tie game?
Like no one scores.
Okay.
Some new, like, better phrases.
What about the level of competition? Maybe they played a really weak schedule relative so that you don't need to score that many points to win. They're still lousy. You play Vanderbilt.
Vanderbilt's good.
Well, not usually, though. It's like the one time they've been good.
When you go to Ohio State.
There's bad teams still, right? What else? Could be as simple as just they got lucky, right? The other team is at, like on the 1 yard line ready to score with time running out and they just fumble the ball, throw an interception, or they, like do something stupid. Sure. Like lots of things can happen. Like you can just get lucky and win a game maybe you shouldn't have won because something, the other team did something dumb or just got lucky, right? Luck matters. Okay. So just kind of thinking outside the box as to like, if something outperforms or underperforms the prediction, like what could have happened? Maybe the predictor isn't that good, right? Like points scored is not the only way to win a football game, right? You could also have defense. Who you're playing matters, right? So, all right. So again, we talked about this idea of a least squared regression line. I showed you, we talked through this earlier, but like here's an individual data point, it's residual. This is me kind of drawing that square. So this is me doing it for all the data points in the data set. Those are all the squares built upon the residuals. And we're looking for the regression line that minimizes the total area of those squares, right? That's what's going on. Just as another visual, we talked about it earlier, but that's the visual. So if you go and you solve this like least squares line optimization problem, it turns out what tumbles out of it is a formula. So to find that slope, you take the R value, that PMCC, that correlation coefficient that we've calculated in the last sections, and multiply it by the standard deviation of y's divided by standard deviation of x's. And that'll give you the slope. And then to find the y-intercept, I take the average of the y's minus the slope times the average of the x's. And that'll give me the y-intercept. So again, we're not going to solve that kind of an optimization problem by hand, but this is the result that kind of tumbles out of it when you do, if you were to do it. And this now becomes just a formula that we can use, right? We know how to calculate all these individual pieces, so we can put that all together. All right, so let's go back to this picture that we've looked at earlier. This is about the car where we're predicting the value of the vehicle based on the mileage. Let's take another break here and interpret the slope and y-intercept in context. Who wants to give this another shot? Let's start with the slope. Great. I would say the only thing that I would say you could do a slightly better on would be saying for each additional mile driven, so like single it, like down to 1, right? 1 mile is basically costing you 16 cents, but that's good. Does everybody feel okay with how Sam did that? How about the y-intercept then? What would you say there? Yeah, basically that's the price of the brand new car, right? Which seems reasonable. I guess this was an F-150. I don't know why. It was a specific to that, but all right. What do you guys think? So far, so good? Okay. So if I want to use the regression line to predict the value of a car with 100,000 miles on it, I basically am just going to plug 100,000 in for miles driven and grind that through the calculator. So I get about $21,967. That's equivalent to just me tracing up from 100,000 to the regression line, then tracing over and reading the value from the y-axis. Is okay with that? Now, are all predictions equally good? Is any prediction we make using a regression line going to be a valid prediction? No. No. There's 2 things that you would want to check to make sure that the prediction that you're making is going to be valid. One, is your regression line even a good fit to the data? Right? If your regression line is like way off what the data is doing, is it going to make a good prediction? No. What was our measurement for how close a line fits to the data? It was the PMCC statistic, that R value, right? The closer R is to 1 or -1, the better your fit. You remember that? So you want to make sure you have a decent fit to make a prediction. The other thing is, what if I said I plugged in like 500,000 miles to this? What am I gonna get? Oops, where did that go? Yeah, so if I plugged in just like 500,000, yeah, right? You're gonna get like a negative number. Does that make any sense? Can your car have negative $43,000 in value? No. No. So, right, what's the least value a car could really realistically have? 0, right? And even at that, like, it's probably $250. I think that's the scrap value for a car if you just junk it. So that's that. So what is the difference between like plugging 100,000 in versus plugging 500,000 in? One of them is called interpolation, and the other is called extrapolation. Extrapolation is the one you want to watch out for. That is not going to make a reliable prediction. That's when you're plugging something in that's like far outside of the range of data values that you use to make your model. So like if I go back and I look at our truck example, my smallest value I have is, I don't know, like 5,000 or something here. That's like the smallest X. And my biggest X is this, like 140,000. So if I'm making a prediction in between those values, it's probably going to be reasonably reliable because this looks like an okay fit model. If I make a prediction far outside of that range of values, though, shouldn't really be able to count on that. And typically the way this works is the further away from the end of your data set, the more extreme value you pick, the less reliable your prediction is. If you made a prediction at 150,000 miles, that's probably going to be reasonably accurate. You do it at 500,000 miles and you're getting the gobbledygook answers coming out. You guys kind of get the idea here? So the two things you want to check is, does your model actually even fit? Is it appropriate to be using this model to make a prediction? And then 2, are you doing extrapolation or interpolation? Because even if you have a good fitting model, if you do an extrapolation, you're probably not going to get a really reliable prediction. Everybody's okay? That's why it's hard to predict the weather, right? Because you're just talking about doing something you based on past measurements and you're trying to predict into the future. Very difficult. We've actually gotten a lot better at it in the last like 20 or 30 years than we used to. But still not very accurate outside of like a week or two, as you guys have seen. All right. That's going to wrap up section 14.3. Let's do some of these in-class example problems. So it says, Carrie and Danielle want to investigate if tapping on a can of soda would reduce the amount of soda expelled after the can has been shaken. For their experiment, they shook 40 cans of soda and randomly assigned each can to be tapped for 0 seconds, or 4 seconds, or 8 seconds, or 12 seconds. Then, after opening the can and cleaning up the mess, the students measured the amount of soda left in each can in milliliters. Below are the data and a scatter plot. So the cans that they tapped for 0 seconds had 245 left after it like sprayed everywhere, and then 255 and 250 and 250 and 250 and 245, you get the idea, right? So here's our scatter plot. And we've drawn in like a best fit line. Everybody feel okay with what you're looking at? Can somebody for me describe the direction, form, and strength for this scatter plot? Positive is the direction. Seems linear to me. Fairly strong seems correct. Everybody feel okay looking at that? Reaching the same conclusion? Pretty easy. All we're doing is really using our eyeballs, right? All right. The equation for that regression line that we've drawn in here, the blue regression line, is given as yada, yada, yada. Identify the slope and y-intercept of the regression equation and interpret each number in the context of the experiment. Who can handle the slope? What does the number 2.63 mean in the context of this experiment?
Or no. Isn't it like amount like times half? You go right now. It's half the time. This is right.
Want to look at the graph or the words? The words? Okay.
Another graph. So basically, for every 60 seconds spent having for every additional 2.60 seconds spent having is an additional milliliter soda as well.
You got it reversed. So for each additional second spent tapping on the can, there is an increase of 2.63 milliliters of soda remaining. So a change in x of 1 results in a change in y of slope, of m, is the way we would say it.
So what do they actually do? Do they put both cans of soda and just
So tapping for 0 seconds is the y-intercept.
Yeah.
X is tapping time.
saying like what are they like, what is the actual experiment? Are they just like
They shook up 40 cans of soda, and then they tapped on them like the top for either 0, 4, 8, or 12 seconds, opened them up, let it spray everywhere, and then measured how much soda was remaining after they cleaned up the mess, like how much was left in the can.
so basically the more they tapped it, the less that came out?
Yeah,
Okay.
which some people think works. I don't know. Does everybody feel okay? What's the y-intercept saying? Good. So if you tap for 0 seconds, there should be 248.6 milliliters remaining. Everybody cool? Probably should include the words predict in there somewhere, but close enough. All right, using the equation above, determine the predicted amount of soda remaining for each of the indicated tapping times, if applicable. Who's handling A? Who's got a calculator out? Somebody get one. Who's doing A? Anna's got it. Who's doing B? You're doing B. Who's doing C? Alessa, you can do C. All right. Yell at me when you got your answer for A.
261.75.
Not what I got. It looks like you might have transposed a number or something in your when you typed it in. Oh. I have the wrong number written down on my sheet then. Oh. I was just looking at the wrong problem. Yes, 261.75. I apologize. I was looking at the wrong spot. B. Who's got your answer for B? Go.
274.9.
Correct. Who's got the answer for C? Alessa.
327.5.
Incorrect.
Alessa.
I don't know what I did.
You didn't make a mistake in the calculator.
328
Nope.
seconds.
Nope.
I don't know.
So, how long were we tapping here?
30 seconds.
What type of prediction is this then? Extrapolation. Should we do this make this prediction at all? No. You should say that this is extrapolation and no prediction can be made with our model. So you should not even type into your calculator. You should say, I shouldn't do this because it's extrapolation. So any prediction would be invalid.
Why is it extrapolation so much outside of
Because our range of tapping times went from 0 to 12. So we should not make predictions outside of that range of values. I tricked you, Alessa. It's okay. Do you think I'm going to try to use this same trick again on a test? Definitely seems like something I would do. So watch out for that. Okay. You can like poke her in the back with your pencil or something. She's going to keep making fun of you there. It's like, sorry, I didn't have the easiest question ever where you just had to plug it in. All right. Next question. It says, from the experiment performed on tapping pop cans, find and interpret the residuals for the indicated cans. So the first one is that the data or the point where we tapped for 4 seconds and had 260 remaining. So that's like this data point right here. Okay. So who can calculate the residual for that? It's just the observed minus predicted. So 0.88 milliliters. So what are we saying here? That this particular situation had this can, after it was tapped for 4 seconds and opened, contained 0.88 milliliters more than the predicted value. So it's like a little bit outperforming its prediction. Sure. Who can do the next one for us? Somebody do it on their calculator. Or all of you that have your calculators out, do it on your calculator. Just get the practice.
Okay, yeah, negative 9.64.
Not what I got.
Extrapolation.
No. I think maybe did you include this parenthesis here?
That's your answer, right?
Did you do 255 at the front? So the actual value is 255.
Can you do it at the end or just
I'm gonna try and do it.
It should be actual minus predicted is the formula.
Negative 14.64.
There you go. Negative 14.64.
all I have it That's just change the sign. All of it. I mean, wow.
What?
If you put it at the end, just all that happens is it just changes the sign.
Right, if you change the order of subtraction, the sign changes.
Got it. So you could, if you like forgot to, you could do it at the end, but you just have to remember to swap the sign.
That seems awfully confusing.
But I got like the same answer, but it was positive.
Right.
So you could like flip it.
Yeah, if you knew that you did it in the wrong order.
Yeah.
Okay. Shh. Is this okay? What does this mean?
It means.
Well, remember, this is not the amount of soda remaining in the can. This is the residual.
It's just less than what, like, it's less than,
So this can of soda contained 14.64 milliliters less than predicted. So if you went back and looked at the graph, I think this is the 8,255. You notice that it's below the regression line. Before, this is the 4,260. Notice that one just slightly above the regression line. So this distance was 0.88, where this distance was 14.64. Everybody feels okay with what you're looking at, what that residual is saying? Okay. All right, moving on here. So let's say we designed a study to investigate the relationship between the row a student is sitting in, their grade on a particular test. We make the row number our independent variable with row value of 1 indicating the row closest to the front of the classroom. Based on our data, we find the following statistics, blah, 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 blah. Use the formulas below to find the equation for the linear regression. Interpret the values of slope and y-intercept in the context of the problem. Who can calculate the value for m for us? Negative 1.12, 3 sig figs. And what's the y-intercept going to be then? About 87 or 85.7? Yeah, Anna. Now who's making mistakes this time? I didn't round my m either. I used the ants command and stored the entire decimal. All right, what does the slope mean in the context? How would we say this? The negative 1.12 is the slope.
So like, is it like for every additional row, like,
Further back into the class you sit,
get lower score?
your test score decreases by 1.12%. No. Well, it says, so the rows are like row 1 is empty, empty, Nora, empty. Row 2 is Ava, Franny, Geraldine, empty. So like, you're talking about like how close you sit to the front of the room, right? What would the y-intercept mean?
I guess you get the front, you get 85.
No. Row 1 is the front. What's row 0?
T-shirt.
You're like on the teacher's desk or something? That's how you do good, right? But that's the idea. If you're sitting in row 0, aka like the teacher's desk, I'm not sure what that means, you'd be predicted to score 85.7 on the test.
You can't even get 100.
Can't even get 100. It's a hard test, I guess.
How do we even do this?
Huh? I mean, I just showed you.
I'm just gonna stop talking. I'm just gonna stop talking.
All right. Let's I want to go back here and do another okay, so for your test, here's the stuff that you should be able to do. Interpret a regression line explaining what slope and y-intercept mean in context. We've practiced that a couple of times. You should be getting better at that and more comfortable with it. Know what changes to the data set do and do not do to affect the correlation.
What day is the test?
I think Tuesday. Give means and standard deviation, or given means and standard deviations for the data set. Calculate the equation of the best fit line. We just did that as an example. Use the best fit line to predict a value. We've done that just as an example. Identify independent and dependent variables for a situation. Use data set to make a scatter plot. Use your calculator to find a mean point for a data set. Use your calculator to complete a table and use those results to find R, like we did on the activity. Use your calculator to make a line of best fit from a data set. That's just using the LinReg, right? Know the 2 conditions for an accurate prediction, that your line is a good fit and you're doing interpolation. Convert raw data to rank order data, and then use that rank order data to calculate the Spearman coefficient. I'd like to do another example of doing that because that seemed like on the test you guys, or the quiz, you guys seem to ask a lot of questions about that and not feel very certain. So let's do that again real quick. And I'll show you some other stuff on the calculator involving LinRegs and stuff. All right. So I'm going to do this example from the second set of in-class examples. So I'm going to start just by entering this data into my calculator, into L1 and L2. If you want to follow along, I welcome you to do so. Clear that stuff also, because I'm going to end up using those guys. All right, so I got my data typed in. Everybody's okay? What I want to do now is I want to rank my X's and rank my Y's. So what I think the easiest way to do that is if I press stat and I pick one of the sort commands. I like to do descending. I think technically Spearman is supposed to be done biggest to smallest. But if you do them both the same way, I don't think it matters. Yep. So if I do sort descending, all it's done is it just put them in order from biggest to smallest. So 71, there's a tie for first. So those guys will both be first. And now I've ranked two numbers, right? I've ranked two numbers, right? So I need to move now to third place, right? But there's a tie at third place. So those will both be threes. And then 169, 168, 167. Oh, thank you. That's good. 5, 6, 7, 8, 9, 10. Everybody okay there? And if I do the same thing down here, it's a little bit easier to do the ranking because I notice there's no ties down here.
What's the R?
Doesn't matter. The definition says a descending. Biggest gets 1. All right. So the problem here is that the rankings that we've given will not give us the correct answer. The problem is that if I add up these where there is no ties, if I add up all those numbers, and I add up all these numbers where I do get ties, I get a different value. So I have to do something different where I have ties. Where I have a tie for first place, those are occupying places 1 and 2. So I have to actually use the average of first and second place. Similarly, where I have a tie at third place, those are occupying places 3 and 4. So I have to do the average of third and fourth place. So it should get place 3.5. Now if I add this up, if I add up all these numbers, I'm going to get the same thing as if I add up all those numbers. Okay? So I'm going to go back to my calculator now. And in list 3 and 4, I'm going to type in my rank order data. So 7, 3.5, 1.5, 8, 1.5, etc. I haven't graded the quizzes yet, I'm sorry. I've gotten behind here. It was on my to-do list today, but I didn't get to done. You know? Yeah. All right. You sure? So now that I have the L3 and L4 into my calculator, I can just do linreg using L3 and L4. And if I needed to make predictions later based on my answer, I could save that into like Y1 or whatever. But I probably don't if all I need is the Spearman number from it. So there's my Spearman. Is that guy right there? Does everybody feel okay doing that? Can I show you something else that's kind of neat? So remember how we were calculating residuals one at a time? I can actually calculate them all at once with my calculator for the entire data set. This is pretty cool. So because I've done my linear regression, I need to do that first. If I go back to stat, and I'm going to clear out, say, L3 here. And inside of L3, I'm going to do second and stat. That opens up the list menu. I'm going to scroll down to names, and I'm going to pick RESID, that's short for residual. So I'm doing it up here in the title. Just says LResid, I press enter, and that is the residuals for L2. Notice that it's the same thing I get if I tried to do it with a formula, right? The residuals is going to be the actual data point, the actual y-coordinate, minus the predicted y-coordinate. So if I do vars, y-vars function, remember I stored that regression equation that I made into y1. So my predicted y-coordinate is just y1 of the values in L1. Notice I get, oh boy, what happened here? No, that's not what I, shut up. Shut up. Shut up. What happened there? Oh. I'm so dumb, guys. I did the linreg on, when I made my regression line, I don't want it based on the rank order data. I need it based on the regular data. There we go. All right. So now if I did that, L2 minus Y1 of L1, now I'll get the same thing as the residuals. Gosh dang it, what did I do wrong now? Oh. All right, one more time. Yes. There we go. There. There, now it's right. So notice the residuals gave me the same thing as if I used the formula for the residual. That's the takeaway. My apologies for stumbling my way through that. I knew you could do it on the calculator though, without having to like do it manually for each one.
Can we do this with like individual numbers too?
Yeah, of course you could.
Do you have to do the linreg first?
Oh, well, if you need the equation for predicting,
Okay.
right?
But like if there's a problem, you just actually
If-
get it, like, go to the
Sure. Yeah. Yeah. Where you couldn't, so Ava, where you couldn't do that is if I didn't give you the data. If I just give you the regression and give you a single data point,
Then you have to do it by hand.
then there's no way the calculator to do the residual.
Data table or everything.
If you give, if they give you a data set, you can get the residuals just with the calculator. Yeah. Yep. All right. That feels good for today. You guys, again, for Sunday, you should complete the 14.3 homeworks. In addition, I need you, every single person in here, to fill out the surveys for your classmates. I've placed the surveys on the My Notre Dame page. If you scroll to the bottom and look at the announcements where it says surveys, there's a hyperlink to everybody's survey. There's like 13 of them or something. It's not bad at all. Do your best with those. Everybody should try to answer everyone's survey. In fact, I shouldn't say try, you need to. Okay? Not all of your classmates are collecting their data from an independent source. They need your help. We're all going to help them. So I need you guys to do that for me today. Everybody okay with that?
One of them isn't a link.
Yeah, that's because I didn't get a survey from that person yet.
Oh.
So when I do, I'll update that. I would also say that, Anna, I think that yours was looking at like Spotify tracks.
Yeah.
I think there's not an option for someone to say I don't listen to Spotify.
Oh.
So you might want to include that as like,
I can look to see if Apple Music does like a.
well, you,
So confused. Joe, does Apple Music?
so,
I have a question about science. It's not